double checking. Oh, there, yeah, it's recurring. Okay, so this lesson's called Hypergeometric Distributions. We're just going to read through some definitions to start, and I'll highlight. So remembering that that word distribution still means listing all of the possible outcomes with all of their probabilities. The hypergeometric distribution contains a specified number of dependent trials. So there's no Bernoulli trials here, having two possible outcomes, success or failure. We still have that grouping of, yes, you satisfy the point of interest or don't. The random variable is the number of successful outcomes in the specified number of trials. So how many outcomes do we want success? Random variable. The individual outcomes cannot be repeated within these trials. The key thing to remember about hypergeometric distribution is that it involves a series of dependent trials, each with success or failure as the only possible outcome. The probability of success changes as each trial is made. So if we're creating a committee and we want to know how many women are on the committee, given a certain number of men and a certain number of women, as I take out one person, that's going to change the likelihood of me getting or choosing or selecting another woman for the committee as my next trial, right? Selecting each person is like a trial in that scenario, because you're not putting that person back in and then reselecting with that person. So there's no replacement. How is the hypergeometric distribution different from the binomial distribution? In the hypergeometric distribution, the probability of success changes as each trial is made, whereas in the binomial distribution, it does not. Binomial is probability with replacement, and hypergeometric is probability without replacement. And here is the formula that we're going to be using. This is really replacing what we did in lesson 1 with probability distributions in that committee question about number of women. We can still solve these problems without this boxed formula. But if we found that challenging back in Unit 1, we can use this formula all the time. Either way, using the formula or just using our kind of logic way of doing it in Unit 1 will both get you the same answer and full marks. So when it comes to this formula, capital X still represents random variable. The little x here still represents the number of successes in the dependent trials. So it's like what we're actually wanting random variable x to take on. How many successes do we want to happen? Little r represents the number of dependent trials. N represents the population size. And A represents the number of successes in the population. So if we were to look back at the binomial distribution, I'm quickly going to just scroll up here. N is the population size in hypergeometric world. N is the number of trials in binomial world. Okay, so those things are switching. So we got to be careful of that. Random variable x is still random variable x, and the number of successes is still that little x, but now N has switched, and we've also layered in A and R. It's almost like that A is what N was for binomial, number of successes in the population, the number of opportunities there are for the success. Okay, so if we have a hypergeometric scenario where we've got these dependent events, the expected value formula is this, right? For binomial distributions, it was just N times P. For hypergeometric distributions, it's R times A over N. And these variables are the same as above. So R is still the number of dependent trials, and A is the number of successes in the population. So we're going to do our examples now and see how these formulas work. Okay, so here's our first example. We've got a box that's containing 7 yellow, 3 green, 5 purple, and 6 red candies jumbled together. And it says already, it gives us a bit of a hint here. The selection process involves dependent events since each candy is not replaced and cannot be chosen again. So whatever I draw out first is going to affect the likelihood of whatever I'm interested in on the second draw. What is the probability of getting 2 purple candies when 3 candies are poured from the box? Okay, so we're going to highlight what we're interested in. What is the probability of getting the 2 purple candies? I'm interested in purple candies, the number of purple candies. That's what I'm going to say what random variable x is. Let random variable x represent the number of purple candies. And for short form, no, I'll write that whole thing out. I was going to write purples. In the past, I've written that. Okay, and we're still going to follow through with that nice numbered set that represents all the different numbers that random variable x can take on. So can we pour out 0 purple candies? Yes. Can we pour out 1? Yes. Can we pour out 2? Yes. Can we pour out 3 purple candies? Yes. Can we pour out 4 purple candies? No. So I'm going to end the box there because only 3 candies are poured from the box. Right. So that's important there. That helps us kind of figure out what all of the different variables end up equaling. Okay, so let's list what our different variables are. So we have A that we need to put in to our formula. We need R and we need S, not S, N. So A, if we look back at the general equation or general formula up here, we've got A being the number of successes in the population. Okay, so that's the number of purple candies in the population or in the whole scenario. So the number of purple candies. So how many purple candies do we have? 5, right? Going all the way back up to the original scenario. R represents the number of dependent trials. So R is really the number of candies poured from the box. And I'm just going to write a little hashtag symbol for a number. So the number of opportunities for success, I'm going to write first. And we talked about that in binomial distribution as well, but back then it was N. So number of opportunities for success is R here, and that's the number of candies poured from the box. Okay, and in this case, 3 candies are poured out, so R is going to be equal to 3. N is the sample size. Okay, and so that's the total number of candies. Okay, so we just have to add up what we've got going on here. It's going to be equal to 7 plus 3 plus 5 plus 6, which is 21. Okay, so those are the values that we're going to put into that general equation, and we're going to solve for getting. Specifically, we want what's the likelihood of getting 2 purple candies, right? So this is going to be what we're trying to solve for the probability of getting 2 successes. So we could fill in the general formula first. simplify here and say it is A, choose little x, multiplied by, and this is n, 21 minus A, minus 5. And then in the bottom of the combination, it's r minus x, so it'd be 3 minus x, all over n choose r, so 21 choose 3. That's just the general formula. You don't always have to write the general formula down. If you went directly to solving for if the random variable x was equal to 2, that would be fine as well. So when we go to sub in, getting those 2 purple candies, we're going to go 5, choose 2. And then in the second combination, well, 21 take away 5 is 16. And 3 take away 2 is 1. And then all over, and the bottom is still 21, choose 3. There's no simplification there. But this is the place where you may have been able to do this using just unit 2 strategies, because the first combination is representing the purple candies, and the second combination in the numerator is just representing the other colors grouped together. So it's like thinking of the first combination as purple candies, and the second combination is all of the other leftover colors grouped together. There's 16 other candies that are not purple. And then in the denominator, it's still total unrestricted, total of 21, selecting 3. So when we figure out what our combinations are, we get 10 for 5, choose 2. We get 16 for 16, choose 1. And then in the denominator, we get 21, choose 3 is 1,330. And then we're going to multiply 160 over 1,330, and we get 0.12. So therefore, there's a 12% chance, and these are very specific, that we will get there's a 12% chance that we will pour out 2 purple candies when 3 are poured out. They're very specific probabilities. Any questions on that? Okay. So the next piece is what's the expected number of red candies among 5 candies poured from the box. So in part A, we were interested in the number of purple candies, and now it's switching to red candies. So that means that random variable x has to change, even though it's asking for expected number. Since it's the expected number of red candies, I have to rewrite random variable x is now representing the number of red candies. And then that little numbered box here, I'm going to go, could we get 0 red candies? Yes. Could we get 1 red candy? Yes. 2 red candies? Yes. 3 red candies? Yes. 4 red candies? Yes. 5 red candies? Yes. Would I go on to 6? No, I wouldn't. Because in this case, I'm only pouring out 5 candies. So even though there's 6 candies in the box, due to this scenario, I can maximum get 5 red candies poured out. Okay. So all of the little letters here will change, right? A is now going to represent Before it represented the number of purple candies. Now it's going to be the number of reds. I'm going to do that in short form. So there's a total of 6 reds in the box. R used to be the number of opportunities for success or the number that's poured out. So in this case, we're still, now it's 5 candies that are poured from the box. Right, it's the number of opportunities there are for us to get red. So that's 5 in this case. N is the total number of candies in the box, so that doesn't change. The sample size. That one's still 21. Okay, and this one's asking to calculate expected value because it says, what's the expected number of red candies? So I'm going to write down the expected value formula, and that is R times A divided by N. 5 times 6 divided by 21. This is 30 over 21, or 1.43, right? It's not a probability. If you're thinking it's a probability, then that would be a problem because we're beyond 1. This is in the unit of the original object. So this is number of red candies. And we're thinking in terms of discrete probability, right? Discrete meaning that whole numbers make sense. So decimals aren't making sense here. So as a therefore statement, I'd accept, we'd expect 1 or 2 red candies. And this is specific that 5 are poured from the box. Okay, I'd accept, if somebody wrote, I'd expect 1 candy, I would take that as correct. If they wrote 2 candies, I'd accept that. I would not accept 1.43 candies because we have to like change it back into that discrete interpretation. Awesome, getting through it. So now we have a card type question. Okay, it's a bit of a longer lesson today. Determine the probability distribution for the number of spades dealt from a well-shuffled deck of cards if 3 cards are dealt. So they give us a little hint here. The selection process involves dependent events since each card is not replaced. Right? Whenever we do not replace things, we're doing hypergeometric, not the binomial. Right? They're no longer independent Bernoulli trials. It's a regular deck. How many cards are in the deck? 52. So that stuff has to come back into play. And it says the probability distribution. So it's everything. It's all of the possible outcomes. And let's start by just saying what random variable x is. So we're interested in, what are we interested in? Number of spades. And that numbered box, right? If I look at the scenario where we've got a well-shuffled deck and 3 cards are dealt out. So when those 3 cards are dealt out, could I get 0 spades? Yes. Could I get 1 spade? Yes. 2 spades? Yes. Could I get all 3 spades? Yes. Probably less likely. I'm going to stop there because only 3 cards are dealt out. I know there are 13 spades in the deck, but that's the scenario, right? They're very specific. So now I'm going to go through and accept that it's hypergeometric. So I'm going to try and figure out what A is, what R is, and what N is. Right? A is, if we look back at the beginning A says it is the number of successes in the population. So if we're interested in the number of spades being dealt, A then is the number of spades in the deck. That's the number of successes there. And that is 13. Hi, Mohammed. The next variable here is little r, the number of dependent trials. So that's like the number of opportunities there are to get that success. So this would be the number of cards dealt. And that is 3. And finally, n is the sample size. So how many cards are in the deck? 52, we said. So the total number of cards. And that's 52. So those are all the little variables that we're going to use in this probability distribution. So we have to do the formula 4 times. There's 4 different values that random variable x can take on, 0, 1, 2, 3. So we flip. There is a little chart there. One of them's already done for us. I'm going to put in this box just the even more specific than the one that's given there. We're going to throw in what we know, right? What we already said. So the A value, if we just go back up a little bit, was 13. So it's 13 choose X. And then that second wider combination was N, 52, minus A, which was the 13. And then R, which was our 3, take away X. And then in the denominator, it was N, choose R. So in the denominator, I'm thinking total unrestricted. If we were thinking back to Unit 2 strategies, we've got a deck of 52 cards and we're dealing out 3. So if we didn't care about anything total unrestricted, it would be 52 choose 3. That first combination in the numerator is representing the spades. And the second combination after we do the subtraction is going to represent all the other cards, all the other types of suits. So if we want what's the likelihood of getting no spades when these 3 cards are dealt, we have to replace little x with 0. And we get 13 choose 0, 52 minus 13, and then 3 minus 0 here. And then 52 choose 3 underneath. I'm just going to work across because it just works better for space. So we're at 13 choose 0. We subtract it within each component of the combination first before figuring out what that combination is equal to. So it's 39 choose 3 over 52 choose 3. Okay, so in terms of just having this probability distribution, I don't need therefore statements. I'm just putting in my little answers within the table. So there's a 41% chance of getting no spades when 3 cards are dealt out. Probability of getting 1 spade in this scenario is already done for us. It's 44%. You guys can try right now doing the one for getting 2 spades. And then I'll put my answer in and you can compare. So I'll give you 3-4 minutes to do that. So that one's about 14%. When we have a probability distribution, when we add up all of the probabilities, they should all add to equal approximately 1. So we can double check that whenever we go through and do a probability distribution, like you probably will on a quiz or a test for this unit. It also says for my next one, what is the probability of at least one spade? Okay, so that wording of at least one spade means one or more spade. So a little bit short form here, that we're going to be greater than or equal to 1. One or more spade is going to be the probability of getting one spade, or the probability of getting 2 spades, or the probability of getting 3 spades. I wouldn't go on to the probability, oh, whoops. I would go on. What is the probability of getting at least one spade? No, I wouldn't keep going on. Oh, sorry about that. We're going to add up those 3 probabilities. Oh. And I can just grab them from my table, right? So I'm going to go the 0.436. Add to it the probability of getting 2 spades. Add to it the probability of getting the 3 spades. That small likelihood there. When we add those guys up, we get our answer of 59%. Okay, and that's when 3 cards are dealt. You could have done that in an indirect manner. This was the direct manner. I think that's the easiest because you've already calculated all the probabilities anyways in the table, but if you wanted to do it in that indirect complementary style, you would go 1, take away what you're not interested in, which is 1, take away the probability of getting 0 spades. Okay, and this last one, what is the expected number of spades? And it says using the probability distribution or using the formula. So if we wanted to use the probability distribution, this is going back to our first lesson, expected value being really the summation of all of the outcomes multiplied by their probabilities. So it would look like the option of getting 0 spades multiplied by its probability. So I'm going to go back up here and grab 0.414. Then I'm going to add to it the next outcome, which was getting 1 spade. I'm going to multiply that by its probability, 0.436. Then I'm going to add to it the likelihood of getting the 2 spades. And then finally getting the outcome of 3 spades, and that each outcome has to be multiplied by their respective probability, and then we add them all together. Okay, so we would expect, now this is not a probability here, this is in the number of spades as a unit. So we'd say we'd expect 0 or 1 spade. That's one way to answer the question. The other way to answer the question is to use the expected value formula for hypergeometric distributions, R times A over N. Right, the sample size is 52. The R was the number of opportunities there were to get that spade, 3, because 3 were dealt. And A was the number of successes in the population, or 13 spades. So if we multiply those two numbers and divide by 52, we get the same answer as our first style of doing it using the probability distribution. Okay, same answer. Both ways are good. One's quicker than the other, I think. Any questions on that? Yep. Yeah, you can use the washroom. It's a lot again, right? It's going way back to a lot of mathematical calculations, but I usually see a lot more success in this unit compared to unit 2 because it's so prescribed. It's like, do this, do that, and the questions are very apparent which style you've got to use, which formula you've got to use. Okay, so the last question that we're going to do is number 3. In the spring, the Ministry of the Environment caught and tagged 500 raccoons in a wilderness area. The raccoons were released after being vaccinated against rabies. To estimate the raccoon population in this area, the ministry caught 40 raccoons during the summer, and of these, 15 had tags. Determine whether this situation can be modeled with a hypergeometric distribution and be sure to justify your answer. So these animals were tagged, they were then released. Then they caught another 40 raccoons to try to understand what the population size was like. So they caught 40 raccoons, and of these, 15 had tags. Is it hypergeometric? So all of the raccoons are individual raccoons, right? When we gather up 40 of these animals and we've selected these 40 from the whole population, when we count the 15 that have tags, when I count one tagged animal, I'm not going to put that animal back into the pen and then recount them, right? It's like you've counted one individual, so now the probability of getting another tagged animal has decreased. So it is a hypergeometric scenario. So let's read through this. The 40 raccoons captured during the summer were all different. They're all individuals. There were no repetitions, so the trials were dependent. The raccoons were either tagged, being the success, or not, being the failure. Thus, the situation contains all the characteristics of a hypergeometric distribution. So we're going to go through here and just try to decide. It is hypergeometric. So when we have hypergeometric scenarios, we have variables A, R, and N. Right? So we're going to try and think about what these numbers that they gave us, how they can match up with the variables within our formula. So A represented the number of successes in the population. Number of successes in the population. That was just in general. What is success here? Let X represent, yep. Yes, the animals that were tagged. All right, tagged raccoons. Okay, so if we were even thinking about this, like, what are the values that random variable X could take on? We could have 0 tagged animals all the way up to what number? 40 potentially, because 40 were caught. So R represents, just in general, the number of the number of opportunities there are to have a success, right? The number of dependent trials. But I like to write opportunities for success. So this value is actually 40, because those are the animals that were caught up. So you could be crazy lucky and get all 40 animals being tagged, but that's probably not the case. And N represents our sample size. No, population size. I should say population size in general. Yeah, population size. And that's what we're trying to figure out. Because it's saying estimate the population. So we actually have to figure out what N is. The final number that was given to us. So we've got 40 in there. How many number of successes are in the population? That's our 500. Should have written that down. 540. We don't know the population size. The last and final value is 15. 15 of them have the tags. And that's going to be the average, or the expected value. Because this formula can tie everything together. So what would we expect to find when we have 40 opportunities for success and we find these 15 actual successes? So I'm going to write down our expected value formula, and I'm going to put 15 into this overall average. That's the number of raccoons, right? Expected value is not a probability. It's in the unit of the original observation that we're making, number of raccoons. R is 40, we said, A is 500, and N we don't know. Population size is what we're trying to come up with. So at this point, we've got an equation with a fraction in it. I'm going to put this whole number over top of 1. I'll rewrite the 15 over 1 here, and I'm just going to multiply that 40 times my 500 to get to 20,000 up top over N. And then at this point, it's just a little proportion here that we can cross multiply to solve. So then becomes 15N equals 20,000. And we divide both sides by the coefficient of 15 to get our answer, 1,333. So based on the scenario of the number of successes in the population and how many opportunities we had for the success, and actually how many animals did have tags, we can use it to then come up with an estimation of what the population size is. So therefore, the population size is about 1,333 raccoons. Okay, so that's it for our lesson today. Tomorrow will be our work period. And you can do the homework for this section, right? The worksheet is in the next page within the One Notebook, and people who are in Class Learner should have that so that already in your packages.